All right, morning everyone. We are a bit late here due to exam, but anyway, welcome to 2025 and the very first seminar of this calendar year, not the academic calendar, mind. We have a guest today, Alejandro Vigna-Gómez, if I pronounce your name correctly, sorry if I do not. And I'll give a word to Reinhold now to introduce our speaker.
Yeah, we have the pleasure of welcoming Alejandro Vigna-Gómez here. Alejandro was a PhD at University of Birmingham in the UK, and then did his PhD there with Gamov and Landau, and so we overlapped at the end of his PhD and the beginning of mine in Australia for a bit. He was one of the early COMPAS developers, worked on binary neutron stars and things related to that. Then he did a postdoc at DARC in Copenhagen, and is now an MPA fellow in Garking. Take it away, Alejandro.
Thanks, Reinhold, and Pablo and Hugh for welcoming me. Very good week, and glad to be here for a second time. So I'm going to talk about the Thorne-Żytkow objects, particularly the progenitors part of them. And it's really kind of a living review on an ongoing quest, because this is a lot of work that has been published in the last few years, particularly last year, or it's going to be published this year. And these subjects have been looked for quite a while. I'll expand on that. But my motivation actually doesn't come from Thorne-Żytkow objects themselves directly. It's more like a byproduct of something else. And I thought it would fit very nice to the region. These I've used before, but from that bit 10 years. And I don't know if you know what's there or you want to guess. If you want to guess, give it a go. But this is The Alchemist. And I bring it up because I usually say this is how we thought about alchemy hundreds of years ago. But now alchemy has this form, which is my preferred and most of my interest, which is neutron stars. Here showing the millisecond pulsar, J0030, which with the hotspots that we can see here and here, probably have to do something with the structure of the magnetic field. We can think these things are not dipoles, which is how we usually model them, and it's trying to give more information about the complexities of nature, here in this case of ultra-dense matter and neutron stars. So why am I interested in neutron stars? I think just by themselves they're interesting, but one of the things is there are sources of R process enrichment through supernovae. Here we have 97A that you can see the before and after in the two panels, of course, but okay, if you need a little bit of help, then here they are, something that appear in the night sky, and that now we can be more confident, or maybe even confirm that in the center there is a dark lens that, or a dark object that it's a neutron star. The other sources of our process enrichment, binary neutron stars, mergers, here an artistic depiction of GW170817, the first of two binary neutron star mergers detected by the LIGO-Virgo-Calgary collaboration, which also enhanced our understanding of our process enrichment and the formation of binary neutron stars. However, historically, we already had some understanding of these from binary pulsars, so millisecond pulsars with a companion that is also of a mass of a neutron star. And in this case, the Holtz-Taylor pulsar that throughout decades allow us to see indirect evidence of gravitational wave emission. And here's kind of where my PhD studies 10 years ago began, because after the detection in 1975, 1 year afterwards, Ed van den Heuvel made some work where he presented the formation avenue of these objects. And this is what I spent doing most of my PhD, trying to understand this formation avenue, is what I'm going to present now, and this is actually how we're going to transition into the Thorne-Żytkow object. But first, I want to show how you form a binary neutron star, and then you begin with a massive binary, where the more massive component here on the left is more luminous and evolves faster, and therefore, if it's close enough to its companion, it can engage in a Rush-Lobe overflow episode, where there is mass transfer from the primary to the secondary, that the primary is stripped, the secondary might accrete some mass, and it continues evolution until the primary, that it's maybe less massive, but still more evolved, goes supernova. And then when it goes supernova, you can form a compact object. For the rest of this talk, we will be focusing on neutron stars. It could also be a black hole. And then you transition to the second mass transfer episode, where now the secondary mass transfer into the primary into the common envelope episode, which will be a big interest for the formation of Thorne-Żytkow objects and also of binary neutron stars that merge within the age of the universe. Because what you want to have is that you strip the envelope and then the orbital period of the binary becomes short enough that eventually you merge within the age of the universe. But before that, you will still have another mass transfer episode where you will recycle the companion, the primary neutron star, will become a millisecond pulsar, observable effectively forever for the age of the universe. Then a final second supernova, after which you form a binary neutron star, and maybe if they merge, a black hole. So this is kind of the anatomy of neutron star binaries, but of course this is not about neutron star binaries, or at least it partially is, but it's about Thorne-Żytkow objects. And the difference is that at the moment of the common envelope, if you have a merger, then you can transition into this other structure. So how is this structure? How does it look like? The most basic picture, and that's how it was probably envisioned initially by Landau, Oppenheimer, and Volkov when they were discussing neutron stars or neutron cores in stars shortly after the discovery of the neutron in the early 30s. Then they say, okay, what if you have a giant or a supergiant, depending on the mass of the envelope, that it's or it was just a star even at that point, with a neutron star core. But it took some time until Thorne and Żytkow started thinking more in detail about this structure. And we will keep it simple throughout the rest of the talk, but you go from having a convective envelope, then to a region where you have an inflowing envelope, up until where you get an E, which is the base of the convective envelope, then a halo, where you have the region of gravitational energy release, which is actually what is allowing you to be in a static equilibrium, and then the further you get in, closer to the center or to the edge of the neutron star, things become more complicated, and eventually you reach the region where you have a neutron star of roughly 10 kilometers. So this is the structure that they solved in the 70s. They found that it was in equilibrium and that it was plausible. And that led to a lot of work and a lot of different speculations, which they actually mention as speculations in section 6 of their paper. So they didn't have a discussion per se, they just call it a speculation. So those were the days, right? One of the things they say is that one of the strongest reasons to believe that stars with neutron cores exist is because everything not forbidden is compulsory. And even when they say that it's extremely uncertain, they say it's fun to speculate. They start beginning thinking, can it be the collapse of the giant star that leads to this configuration? Or can it be that the neutron star is forming a closed binary system spiraling into its companion interior? So effectively, these first paragraphs of this speculation section contains the bulk of this talk and the research that has been done around it. So what are the formation scenarios? The formation scenarios are the following. Let's say three main. The first one is the collision scenario, where you two have a head-on collision of a neutron star and a star, and then they form a Thorne-Żytkow object. Kind of easy and clear. Then the one that we're going to be focusing a little bit more is the binary coalescence scenario, which follows after the common envelope and with the formation channel that I was presenting a little bit before. And there's another one, which is the supernova kick scenario, where you have the pre-supernova star and then a star companion, but then when the supernova occurs, you get a kick, and if you get it in the right direction, which is opposite to the orbital velocity, then you can kind of go back and then have a major main sequence companion and then have a head-on collision in this case. So this is roughly the three formation channels, but however, and the rates of these from the literature are the following. Collisions are rarely revised and usually assumed to be very small. The coalescence scenario is generally assumed to be the dominant one, but there's a lot of caveats that we will go into. And then the supernova scenario, which is slightly subdominant to the binary coalescence, but maybe it's a little bit more straightforward. So with these rates in mind, I want to highlight that there are two possible configurations of collisions and the post-supernova scenario. that are not effectively head-on collisions and lead to more like a tidal capture or so, and they kind of blur the lines and map back into the common envelope scenario. Maybe not identically, but the point is that you end up having a capture, and then you're embedded in an envelope, and then you have the merger. So it's kind of like a combination of these two scenarios. Okay, so we go back to this diagram, and I'm gonna put it a little bit on the side so you can follow it, and in case you get lost, because we're gonna go sequentially through some of these and back and forth. And we're gonna begin from the middle, so the moment where we have progenitors that we consider to be Thorne-Żytkow objects. And this is based on some work done by a graduate student, Kyle Nathaniel, who is at Rochester Institute of Technology, wrapping up her PhD. This is using COMPASS, which is Rapid Population Synthesis Code, using the stellar models or fitting formula for stars by Hurley et al. 2000, and a lot of the binary prescriptions of Hurley et al. 2002, if that says something. And what we do here is each dot in this HR diagram represents a stellar donor that has a neutron star companion that has been determined to lead to a dynamical and stable episode and engage in a common envelope phase. So these are potential progenitors of Thorne-Żytkow objects. There's two colors, so the red or brown one is depicting the ones that COMPASS determined to merge. So we say, let's consider they will all be Thorne-Żytkow objects. And there's the other one that are the ones with more elongated envelopes, where are in the lighter yellowish beige color. And we say those will eject their envelope, and they will become short-period binary systems, potential progenitors of binary neutron stars and binary neutron stars mergers. In this plot, we have other things. So we have the zero-H main sequence line, the terminal H main sequence line, a couple of tracks of single-star evolution of 5 and 20 solar masses. And additionally, we have these strip helium stars. I will not talk about this now, but mention them later, so just forget about them for now. And we have the histograms showing the rays as a function of number of systems over number of core collapse supernovae, highlighting those that COMPASS predicts to become Thorne-Żytkow objects and those that end up in a short period binary following the common envelope. Moreover, we highlight and we start to investigate how many of these systems actually experience a mass transfer episode, and we find that the vast majority, so that's the green line that we see here, is saying how many of these systems actually go through a mass transfer episode, and it's the overwhelming majority of these systems. What are the implications for these things? There's two that I want to highlight first, and it's one, mixing and composition. So this is some work done by Mathieu Renzo and Ylva Goldberg in the context of set of Yuki, where they show for different element abundances in each of these rows, how, for example, rotation affects mixing, and then they contrast it to a binary accretion model, where you can also spin up the accretor through a rotation, but the point is that it's a self-consistent binary accretion model where then you can follow up. So let's see, for example, what happens in nitrogen. The symbol here is the observed values for set of Yuki, and then we can see that as you increase the rotation going from left to right on the columns, then it starts increasing, and at the end it becomes similar to the one of the binary that predicted from the binary models. So there's some certain degeneracy there between rotation and accretion that it's not completely unexpected, but it's highlighted here. In color is showing the age, but moreover I wanted to show how a composition is varying, and therefore the rejuvenated donors that will eventually become the stars in the common envelope, they can be having some sort of mixing and anomalous composition. The other thing that this mass transfer does is it affects the binding energy. So here we show the mass coordinate and the binding ratio of the binding energy as a function of radial coordinate, and particularly if you see the rejuvenated, in other words, that has experienced a mass transfer episode versus the non-rejuvenated model that hasn't, one can see that the ratio between them is always below 1, and that suggests that there is a decrease in the binding energy, particularly it's very sensitive in the region between 1 and 10 solar radii for this model. That's a very important region because it coincides in this model and probably in many others with the region where we have the hydrogen burning shell. So in this plot where we have mass coordinate and radial coordinate on top, and we have the binding energy here as a solid line, and the hydrogen mass fraction as a dotted line, we can see that between the helium core and the convective envelope, we have this region, and that's where the binding energy drops by 2 orders of magnitude. So if you're changing the structure of this region, you're also potentially changing the binding energy. And the binding energy is crucial to make predictions about how much mass you can eject and whether or not a system will become a merger. So I want to highlight that there's 2 things from mass transfer that we can affect, probably more, but the 2 are changes in composition of your star and changes in the binding energy. And when people do simulations of common envelope evolution, you don't always include that because a lot of people use single stellar models. One person that didn't do this was Camille Landry, that recently started here. So she has a simulation addressing these things. I hope she will be able to present it at some point, or she probably already did, with some very nice results. Okay, we move forward in time, and then we go to the moment of the supernovae. So when the supernova occurs, there's a couple of things that one can easily think it will happen. The first one, the binary becomes disrupted, and now you have a star and a neutron star. So therefore, no Thorne-Żytkow object, no binary neutron star, just 2 disrupted isolated objects going one way or another. And the other one is that the binary actually stays bound, right? And here, this is a paper where Ryo Hirai and Philip Podsiadlowski performed 3D hydrodynamic simulations of the collision of these binaries due to the supernova kick. And here's a particular slice of the parameter space where we can see that for a binary with these properties, we get different possibilities, right? Like we get that there's an unbound with no collision, bound with no collision, bound with penetration, etc. So depending on the pre-supernova orbital velocity, if you have a very large natal kick, then you will most likely unbound without a collision. That's kind of intuitive in a way, I think. And if your natal kick is very small, which is the other regime, you will remain bound without collision. And when you have natal kicks that are similar to the pre-supernova orbital velocity, then you start going to a regime where different things happen. You're usually always dominated by the unbound, no collision, so usually you just unbound the binary unless you're in this limit. But then things start happening, and you have the possibility of having a penetration onto the star that doesn't lead to a Thorne-Żytkow object. Sometimes it's disrupted, and sometimes it stays bound. And these are like the kind of like blurred lines that I was highlighting that here are shown in a quantitative way. And then you have the case of the immediate merger. So this light blue cyan region highlights where you could actually form a Thorne-Żytkow object from the supernova scenario. Of course, this is a small part of the parameter space, and that's why also the rate becomes so low for this thing. And one could also see that this plot changes as a function of the binary orbital parameters, and the assumed natal kick distribution, or the given natal kick, but it gives an idea of how small this parameter space is in order to form a Thorne-Żytkow object directly from collision. Okay, now that we have an idea of what could have happened with the mass transfer episode and the supernova, we transition onto the common envelope evolution, which is extremely complicated, and I will probably just skim over some of the many details that are there, but I want to highlight this work by Rosa Everson and Tenley-Huntington-Smith, where actually these are simulations from Tenley-Huntington 3D, where the main comparison is top and bottom, seeing how does the stellar material, here particularly in yellow, is affected by a companion, a compact object companion, which is the white dot, in this case a black hole, and in the bottom a neutron star, and how, in this case, the black hole is disrupting the core quite early in the evolution, while in the neutron star, the core remains more or less intact. And with this simulations, or like inspired by these simulations, the group of Enrico Ramirez-Ruiz, which is effectively these two, and I was also part of that, they came up with a simple estimate of when would you get a core impact and a core disruption that has to do with the tidal radius. So they just compare the radius of the core to the tidal radius. Oh, sorry. Oh, yeah. The neutron star that was born relatively recently potentially has a magnetic field and is potentially non-negligible. This is generally not accounted for in most simulations that I'm aware of. So that's a caveat. But the point is that with this comparison between the tidal radius and the radius of the core, using MESA models, which are the dots in this diagram, we see in the mass radius parameter space some predictions of what can happen to these objects. So for example, if you're very far away in a very wide binary, then you end up in the common envelope regime that can lead to an ejection because the envelope is loosely bound. So if you go up here in radius, the binding energy is dropping, and when you are very expanded, very fluffy giant, then it's maybe easier to eject the envelope than in previous phases when you are more compact. And then using this criteria, we can see the two regions where we have the core intact versus the core disruption. So the core is disrupted for these less massive systems, and for the more massive, it might remain intact, again, for these considerations. But even when the region of the intact core is larger, remember that this is probably weighted by the IMF in one way, so you're more likely to have things that are with less mass than more mass. And then the comparison was done for a black hole and a neutron star model, where the black hole is disrupting more systems because the tidal radius is bigger. So one of the things that comes from this study is that maybe you get a lot of disruptions, and maybe having a core intact is not so easy. What, besides the fate of the core, is important is also if you can form an accretion disk, and that has to do with the angular momentum reservoir of these objects. So the core, if you think about it as a non-rotating core at the onset of the common envelope, and then you put it in this simulation that it's going to lead to a merger, that's similar to what you get in this plot, where you show as a core mass, or core mass fraction, I think it is, as a function of the angular momentum over the angular momentum of a disk at ISCO. So the point being that these lines evolve from bottom to top, they go from 10 to 5 to 2 tidal radius, and they are being spun up by shocks, and therefore the core that was initially non-rotating becomes highly rotating. And then if we compare a MESA model with the assumption that the core will be critically rotating at the moment of merger, it looks like this solid line. So you are effectively spinning up the core, and if you spin up the core and you have enough angular momentum, then you will form a disk. And when you form a disk, all of the material that you have not already swept, which you might have a lot during the disruption or so, then you can provide additional feedback that can remove it. So the caveats here are that the merger process itself, it might be not very good for keeping a structure as the one envisioned by Thorne and Żytkow, where you have a very nice, big, fluffy convective envelope embedded in a neutron star. You probably have ejected fraction of the envelope in the merger process. For completion, I will just briefly show the morphology of the ejecta. It's, I would say, unsurprising. This view, you're seeing the binary like this, and then you can see that the ejecta has a somewhat toroidal structure. This is the same if you see Camille simulations, both with rejuvenated and non-rejuvenated donors. So it's just to give an idea of what maybe would happen to the ejecta at how would the ejecta look at late phases of the merger? Not the merger itself, because then you can still get additional ejecta, but it's something like this. But well, now that we have gone through some of the caveats, I want to go back to this plot and now make some additional comments. So the main comment is that if we include in this plot the symbols from the paper by Everson, which were in one of the previous plots of the mass and radius diagram, they look like this. So they're spanning a lot of the main sequence and a little bit of the giant phase. And then if we use their criteria for tidal disruption, we just color them a little bit differently and see that these things are green. The main point of this is to show that actually our initial configuration was probably a little bit optimistic. It's optimistic because the things that are going to lead to Thorne-Żytkow objects, we know that they have been rejuvenated, so maybe the binding energy dropped, and maybe they are not going to lead to a Thorne-Żytkow object, but more like a short period binary. We also can consider that a fraction of these will have their core disrupted. Probably a big fraction of them will form an accretion disk, and therefore it will remove. And it's generally complicated, but the way that I see is that the results from this work are providing like an upper rate estimate, and then things can just become smaller. So in other words, what we are currently predicting, which matches what it's in the literature, it might be optimistic, and this thing can just, that's as good as you get. It was 10 to the minus 4 per year, roughly, order of magnitude. Okay, and so a little bit of comment about the rates of this thing. So here we're showing this as a function of the rate of core collapse supernovae, and the point being that you have all the systems that go through mass transfer, and then the fraction that have a neutron star companion, and the fraction that are rejuvenated. So you can see that rejuvenation is occurring in a lot of these systems, and particularly in the mergers. The point is that maybe if the binding energy drops, then you move some things from this box to the common envelope ejections box, and that's how the rates decrease. I'm gonna skip the next slide, but if you wanna ask me about these during the questions or later, we can go through it. It's just depicting the growth of the convective envelope of a massive star. But with this in mind, I will go now to back to the strip helium stars, to the helium Thorne-Żytkow objects. And this is something that we found in our population. And the thing that happens is that you have a successful ejection, and then there's a merger in the last mass transfer episode. So these rates are relatively low, so it's 10 to the minus 5. So you would really need to wait. And they, again, might be optimistic. So how do we assume if these things will actually form or not? We compare the response of the radius of the donor to the response of mass loss. And this is very simplified in the method of compass, so take it with a pinch of salt. But the idea is that if you, depending on how your star responds to mass loss in radius, and depending how your orbit responds, then you will be favoring a merger or not. So for example, if your star contracts and your orbit widens, so something like this, then this is likely stable. If it's the other way around, if your star is expanding and your orbit is shrinking, then this is leading to an unstable mass transfer episode and runaway scenario that ends up in a common envelope phase. So we use this and we get these things. Believe it or not, when we compare this to detailed models of adiabatic mass loss, we do find that they do not pass the test, and therefore this, from using the criteria based on mass ratio by Ge et al., none of them actually does, but we were not expecting them, and we highlight them in the paper to think, okay, these are rare, but maybe they're extremely interesting. So something to keep in mind, but yeah, more rare than your regular Thorne-Żytkow objects. So if these are already quite exotic, then yeah, maybe not that. We move then to see, okay, if composition is not the smoking gun signature, and if also there are uncertainties on the supernova aspect of it, okay, what can we say? Can we say something about the kinematics of these objects? And doing that, what we try to explore is what is the center of mass velocity, the distribution that we get after the supernova, assuming that there's not going to be much change when the common envelope begins, and if actually the Thorne-Żytkow object forms, that there's also not going to be more change. So there's some assumptions here, but we just wanted to explore if we could say anything about kinematics in this velocity versus mass plot, and the answer is kind of no. We have also the histograms on top and on the right, and the answer is no because these are different, like the rate of unbound main sequence stars is orders of magnitude between 1 and 2 larger than the rate of the Thorne-Żytkow objects. So if there's any overlap in these histograms, then the unbound main sequence stars dominate, and actually you wouldn't be able to see the TCO main sequence progenitors, which is where we're not plotting them. We're planning with normalized both instead of on the same scale. So we don't focus on the subtleties of the structure, but more on the broad region, and then we see that it's fully covered, there's a degeneracy that we would not be able to resolve. The same thing happened when we consider pulse main sequence donors, which maybe here you can get more excited about this tail, but again, as I said, the purple is dominating in the absolute rates, and therefore it becomes negligible. And okay, maybe it changes a little bit in the helium main sequence donors, the helium Thorne-Żytkow objects, because there's a little island here. But as I said, take this with a large pinch of salt, and maybe just put it in the background of your mind, and yeah, don't spend your career on them. Okay, so now we've gone through a lot of these phases, but I want to go to the second, shorter part of my talk to discuss a little bit what are actually the Thorne-Żytkow objects and how can they evolve. Admittedly, this is not my area of expertise, and I've been working a lot on trying to understand it a little bit more, but I think putting them out is a very useful thing to do in order to hopefully communally get a better understanding of these things and solving some of the key questions. The more basic approach to this is to go through the canonical evolution, which is quite complex in itself. So this is an HR diagram of from Farmer et al. 2023, showing the evolution in colored lines here, which represent the mass of the Thorne-Żytkow object as a function of time, seeing that they become less luminous and they evolve to the right here, right? And all of them are doing that. The more massive ones are longer lived. There's some observations in gray region and in this dashed line, but what I want to contrast with is these white lines. So these are straight lines. There's an actual stellar track behind these that is very thin, so I just put a straight line. But these are actually very different, and they're evolving upwards. And these are the solutions from Canada et al., that seminal paper in 1992 using the STARS code. So when Rob Farmer put this out, I never fully understood the difference between these models. It has to do with how you build the structure. I don't understand why one evolved which way. But I was thinking, okay, there's been so many years in differences. They're using different codes, okay, it's different, fine. Maybe we will not know why. Maybe we will. But just Monday, I was reading this thesis that I discovered at some point by Hackett et al. So Alexander Hackett is a student of Chris Stout, or was, that graduated in 2023, and that he put his thesis out at the same time that Rob put his paper out. None of them actually cite each other, and they don't discuss each other's work. I don't know why. But the interesting thing about the Hackett thesis, which is a very comprehensive study that I would recommend as a review of Thorne-Żytkow objects, is that he actually incorporates the same model from Canada et al. Into MESA, and he finds effectively the same solutions. So now we have actually two models. You can think of this as the Hackett models, and they're both using MESA, and it tells us that the difference is, okay, I don't know which version is MESA, but the difference is not in the code itself and the numerics, but more in how do you define the structure of a neutron star and the Thorne-Żytkow object. And that, I think, is an open problem that will probably can determine how interested these objects are or not. Because from the models of Farmer, we get evolutionary lifetimes of 10 to the 4 to 10 to the 5 years. But from the models of Hackett and Cannon, it's 1 million years. So you're going from something that makes kind of irrelevant these objects or very fortuitous events to making them actually there could be hundreds in the galaxy. And this is a potential interesting avenue for developments into really understanding these things if they form at all as they are modeled. So that's another caveat, right? The other thing that has been recently proposed is this work by Enrico Ramirez's three students, where they say, okay, you will always form an accretion disk, you will always either disrupt or eject most of the envelope, but what if you actually retain a little bit of an envelope that is roughly 1 solar mass diffuse in a similar surface than you have the that a regular Thorne-Żytkow object would have? I actually don't know how this would look in the HR diagram. Pablo was asking me about it, and I don't know, and I haven't seen it or thought about it in detail. The idea is that you will have energy generation that could make you X-ray visible for 1 million years or so. So the idea is that they are not quite Thorne-Żytkow objects, but maybe similar. So this is something that was proposed last year, and that maybe a configuration also worth exploring. The thing that we recently worked on, particularly Pablo Martinez Mirabe, who is a postdoc at the Niels Bohr Institute working with René Tambora, was what about neutrinos? So can we say anything about neutrinos? So following the model of Chevalier in 1989, where we can assume in different regions of the Thorne-Żytkow object, which is just a neutron star core with a burning shell and then a convective envelope where we have different temperatures each. What is the rate of expected neutrino, thermal neutrino emission that we think we would have? So I think maybe from this plot that we show, okay, radius and temperature, the key is that you will have very high temperatures, and that's good for neutrino emission. And then we go into this bottom plot, we can see that the models that begin at the core of the neutron star, here's a star, go to the surface, and then there's a region where the models live where you can have a neutrino emission from per-annihilation, depending on the mass accretion rate that you get. So with these estimates, Pablo came up with two potential observational avenues. One of them is, what if you have a steady Thorne-Żytkow objects that are accreting at this rate? And the other one, what if you have more like a burst, so you accrete at extremely high rates, like these are also quite high, these are all above Eddington. What if you have these things at even higher rates and they're just a burst, and could you detect them? He did this in the context of, here is Juno and Super Kamiokande and Hyper Kamiokande, and here is Ice Cube, Super Kamiokande and Hyper Kamiokande. But the point is that generally, as a function of distance, you need to be, the closer you are, the better, and then the higher the accretion rate also, the better. These are very high accretion rates, so one thing that can happen when you are in this regime is that your accretion becomes very efficient into the neutron star, because now you're in the neutrino regime, where that allows you to get rid of all the additional energy, and then you would collapse into a black hole. So in principle, some of these bursts could be interesting, because then you can see a neutrino signal, and then it would disappear eventually. So you would lose the neutrinos, but again, you're thinking about very high accretion rates. So I am a little bit of a cynical, so I would say that you will not see anything, and then you can put the upper limits on these rates. Also, in the burst scenario, you are relying on having a formation in the next 10, 20, 30, let's say 100 years. So you're relying a little bit on luck. And like Hans Thomas Janka said when I presented these results with him and discussed them, he said, I've been waiting for a galactic explosion my whole life of a core collapse supernova, and at the end of my academic career, I'm not there, so good luck. Okay, so yeah, so I'm about to really wrap up, just showing here some of the candidates. Maybe I'll actually just gonna skip it. We can come back if there's some interest. But the final thing I just wanna mention is how does this propagate to the formation of double neutron stars or double compact objects? Another thing that we got in this paper, just kind of making the counts, counting the systems with the population synthesis, was the effect of rejuvenation, to find that the rate of double compact objects in maybe funny quantity, so here's again in the core collapse supernova rate, number over number of core collapse supernovae, usually you get predictions per gigaparsec cube per year or so, but then we have that most of the systems that are binary black holes, binary neutron stars, or neutron star black holes that merge within the edge of the universe have experienced rejuvenation. So if you are in this regime where you are like with those symbols, then there's rejuvenation, and then this is regularly not accounted for in the literature or in the simulations. So to finalize the summary, we have a review on these Thorne-Żytkow objects led by Anna Grady for the Encyclopedia of Astrophysics, but I think also the PhD thesis by Hackett et al. Serve as a very complementary, important piece, because that's not published as a paper, so it's a bit different, but it's very thorough and very good. I don't know if it's going to be a paper. I hope so. And just to summarize the formation scenario, there's three things: binary coalescence that inherit all the caveats from binary evolution, collisions with or without tidal capture, pulse supernova collisions that might work, but the rates are uncertain, and the collisions in dense environments are rarely studied and always neglected. Mass transfer can lead to changes in composition, a drop in the binding energy, so that is there, but it's also degenerate with the stars that become unbound. So if you find a star that maybe has some of the imprints of a previous mass transfer episode, the likelihood that it's just an unbound star is more than it actually eventually merge with a neutron star. The kinematics are overall degenerate, so not much to do there. And what are new things about Thorne-Żytkow objects? Well, one really needs to understand the structure. That's, I think, this Hackett really points out that this is extremely important in contrast to the work from Farmer. The observable item is key. The longer you can observe them, the higher the rates of observation or the probability of observation. Maybe these things are actually not forming as Thorne and Żytkow envision. Maybe they're slightly different. Maybe thin envelope TؐO, maybe something else. And detection via neutrinos is dependent on the mass accretion rate, effectively. But yeah, we'll see. There's, I think, a lot of things to do and understand. And yeah, and I didn't even talk about the observational composition problems and discussions that usually arrive around these subjects. So thank you.
Thank you, Alejandro, for a very enlightening talk. Time for questions. We have time for several.
Thank you for the very nice talk. I'll actually ask about the thing that you had skipped at the end, the observational counterparts. So people have been looking for these for a while based on the sort of the rare nuclear isotopes that you expect from the fusion in the core. I hadn't realized that so many of these are expected to be rejuvenated stars or helium stars. I'm wondering if the searches for these unusual isotopes are focused on the wrong systems, if we should be looking at things that a priori look to be rejuvenated or are helium stars for these rare isotopes.
Yeah, so I think it's both. So so I'm not an expert on that, but from what I know, most of the searches have to do with the search for the materials that have experienced the interrupted proton capture process, and that's because the energies that you get in the knee, in the base of the convective envelope of the star and a little bit below, we are like very high, and therefore you can begin the proton capture thing, and then as convection drives you out, you beta decay, and then you interrupt it. So there's like, that's a nucleosynthesis part of it that has to do with really having very large temperatures or high temperatures in the vicinities of the neutron star, in contrast to the nucleosynthesis from changes in nucleosynthesis from accretion. So I think in principle you should have both. I don't know if there's something like if you combine both you get something very peculiar. I don't think that has been done. I don't know. So I hope that's yeah, something that people either are aware of or are working in. But yeah, my point is that there's two different things. They're probably both present, and I'm not sure if the combination has been addressed.
Thank you.
Questions?
Hi, thank you for the very nice talk. My my question's on page 16, I think. You had a graphic there.
Oops, sorry. Yes.
Next page, I think,
Yeah.
is this one. So two things. One, the vertical axis, is that just, I thought at first that's mass ratio, but no, that has to be some sort of population fraction or...
Yes, indeed.
Okay.
Yes.
And second of all, can you talk a little bit about how you would expect this graphic to look for the analogous plot of different mass ratios instead of it for this particular mass ratio?
Yeah. So I think there's two things. One thing is the mass ratio, but the other thing is also the separation. So I think depending on separation, like if you make it wider, then you're probably going to this regime, and if it's easier to disrupt things with a given natal kick and so on. With the mass ratio, so if this, I guess what I'm thinking is that you would generally have a range of companions because you have rejuvenated, so it can be that your secondary is more massive. It can also be that it remains less massive. I think generally you will always have the unbound no collision dominating, to be honest. Like, I don't think this will grow a lot. So I think this will probably remain around the pre-supernova orbital velocity place, which will shift depending on your mass and separation. Then you will have like this little pocket of the penetration and the direct collision, which is kind of the solution that you get when you kick behind and you have a little cone and then you hit in. But everything that is not that, it's either just going to make your orbit wider or disrupted. So you're kind of going to be moving this little pocket around, but I don't see that it will become very large. If you get very close, then maybe, but if you get very close, also you need a large kick. So like this value grows, so then there's like a reweighting of the distribution. Yeah, sorry, I was not more fluent, but I hope at the end I gave an idea.
No, that was great, thank you.
You have more questions?
Hi, Alejandro. Yeah, I was wondering about how these objects die, actually. So is there a bright transient, or is it more like the unveiling of a white dwarf? Is it just blowing away the remaining envelope and exposing the neutron star?
Yeah, so also open for debate. I think some people consider that you can get a very bright transient from the accretion that then can kind of like the accretion disk can really power up a lot of the remaining envelope, and then you can get something like maybe a superluminous supernova kind of thing. But I'm actually not super convinced that which way it goes. I do think that once you get very high accretion rates, it will be inevitable to form a black hole. So the question is like how quickly you become a black hole, and then if that's the case, you can probably remove a lot of energy of the envelope. But it's how much of the envelope remains before you actually end up your life. And that's under high accretion rate assumptions. The other thing is if your accretion rates are low, then you just start pulsating, and then eventually you just poof. And that's what the models from Farmer et al. Show. So if you see those models, like you get the pulsations.
Okay, and if I can have one more question, I guess. If it turns out most of these systems are in triples, do you expect that to dramatically affect your results?
Yeah, so it depends on what type of triples. So there was this paper by Nora Eisner, Cole Johnston, Sylvia Tonnen, where they actually find a triple that is 1-day orbital period, 6 + 6 solar masses-ish, with a I think it's 50-day orbital period, 16 solar mass tertiary. And when they forward modeled with Sylvia-Tonen's code SEBA, they found that this one merged, so it reduces to a binary, and then you will have mass transfer from the tertiary into the inner binary, which will, they say that could lead to a common envelope, for example. So there's configurations like these ones where you just, a triple just reduces to a binary and then it goes forward. And okay, the things that can change in a merger is that then you can make the star magnetic or so, and that can change things a little bit. But for the 0th order, I would say they will just reduce to a binary and then you can still model it like this. The other thing that can happen when you have a triple is that you can maybe have collision similar to the supernova, or maybe an exchange that then a configuration that would not have formed a Thorne-Żytkow object, then you exchange, you get rid of a star, and then you form a binary, and then again you do. So I think it's kind of in the line of lines being blurred, like mapping other multiple configurations to configurations that we already know, either tidal capture, either we know exists, we don't know how they work, tidal capture or binary coalescence, but as of now I cannot think of a very peculiar signature from triple evolution.
Thanks.
Do we have any more questions? Yeah.
Hey, just a quick one on how you turn your n over n neutron star into an actual rate. So you're just multiplying by the core collapse supernova rate in the galaxy for that? I guess 10 to the minus 2 per year?
Yes, the value R is just from the from COMPASS. So we know how many systems form a TǳO according to us, and then we have a number of systems that form a neutron star or a black hole with fallback less than 1. Then in order to go to that, we assume a continuous star formation rate. I think it's 2 solar masses per year, continuously in the galaxy. Or we can also, because then we assume that the core collapse supernova rate is 1 per 100 empirically, and that's how we combine the rates.
Okay. So then it's from the binary systems where you have 10 to the minus 4 per year, that if you think if they live all of them for 1 million years, you would get 100 in the galaxy.
Exactly.
And then if they live for just 10 to the 4, you just get 1.
Yeah.
Okay.
So I'm an observer, as you know, right? Assuming we find one, or we kind of more or less convinced that we found one, what would be the most interesting observational constraint that you would like the observer to provide? What would we learn? Or what should we focus on? Rather than saying, well, fine, those exist, we have them, we can tick that box, but then?
So what I would be interested is, okay, to observe them, I think one way it could be like doing different asteroseismology models of the structure, see if they differ, for example, grabbing 2 different models, and then see if then you can pinpoint one. The things that it can provide constraints is in the nucleosynthesis via interrupted proton capture. I think that's something we can learn about it. Potentially neutron star equation of state, like an additional constraint to that. And maybe in the accretion, like accretion onto neutron stars in these environments. So once that you figure out that, if you're convinced that this is actually that, those are 3 things that I think one can learn from. Probably more, and I'm not sure, with these things, I think it's more realistic to think we'll find some rather than thousands. So I think it would be a more case-per-case basis, and some of the limits of astrophysics and ultradense matter that way.
Thanks.
All right, we are at the hour. Let's thank our speaker again. And I believe Alejandro is still around this week at least?
Today, and I'm leaving tomorrow morning. So.
Okay, so if you still want to have a discussion with Alejandro, find him today. And thanks for coming. See you next week.